Based on the discussion board for the Rotational Collisions Lab, I want to take a few minutes to talk through some ideas from Part 2, which this is the portion that asked whether where the marble strikes the block has any impact on whether the linear momentum is conserved. So I'm going to go ahead and start with an SOS diagram for two scenarios. And in each case, I've got the block initially at rest, and then that block had a stripe on it that indicates where its center of mass is. And because the block tends to rotate around that center of mass, it makes sense to treat that as the axis of rotation for the purpose of thinking about torque. So the first one I'm going to think about right now is when the marble comes in and hits that center of mass directly. And so there is no distance between the axis of rotation and where that force from the marble is applied to the block. And so there's no torque applied by the marble on the block. And then the other scenario I want to think about is when the marble hits near the top of the block, far away from the center of mass. And so then the R is going to be relatively large, and the torque is going to be something greater than 0. And you probably noticed in the video that in this first case, when the marble hit very, very close to the center of mass of the block did not rotate much after the collision. Whereas in something more like this second case, where the marble hit far away from the block's center of mass, the block rotated a lot. The next thing I want to think through is an interaction diagram. Now, for the purposes of this, I am only going to think through the horizontal forces and the horizontal motion, because neither object begins with a vertical velocity. They're not moving up and down at all. While there is an unbalanced force of gravity on these objects once they're in the air, the time we're looking at is incredibly small. This was recorded with a high-speed video, and so we're looking at a small fraction of a second. And so these objects gain almost no vertical velocity, and therefore almost no vertical momentum in the time that we're looking at this over. However, that marble, because it's launched pretty fast, starts with a lot of horizontal momentum. So I'm only going to think about the horizontal for the purposes of this. So at that moment of collision, there's a normal force between the marble and the block. I'm going to go ahead and make my system the marble and the block. So I've got the block-marble system. Now, what that means in terms of the initial scenario here is that the initial momentum of the system has to equal the initial momentum of the marble. Because the block does not have any initial momentum, the marble has all of the system's initial momentum. Now, these interactions aren't any different based on where the block hits. We're assuming it applies about the same force to the block no matter where it strikes. And so, the interaction diagram is identical for both of these cases, no matter where the marble hits. Now, if I think about the after, in both cases, if I'm only thinking about the linear motion, the block ends up with some linear motion to the right, whereas in just about every case, the marble bounced off and moved to the left. And that's the same whether the marble hit near the block's center of mass or whether it hit near the ends. And so if I want the total momentum of my system, that has to be the final momentum of the block, which I'm going to call PFB for now, minus the final momentum of the marble. So the way I approached this question is I said, well, if linear momentum is conserved, that means this total final momentum of the system should equal the total initial momentum of the system, no matter where the marble strikes the block. And in terms of my interaction diagram, since this doesn't change, I don't see any reason for the linear momentum to change. So I'm expecting it to be conserved since there's no impulse acting on the marble and the block, or on the marble block system. So what I did is for each collision, I found the speed of the marble before the collision. I found the speed of the marble after the collision, and I found the speed of the block's center of mass after the collision. So for each object, I measured how much time it took to travel a certain distance. Because I'm assuming the velocity is constant, I was able to do distance over time. So none of these objects, aside from during that moment of collision, have any horizontal forces. So it's a reasonable assumption that they have a constant horizontal velocity. And there's two ways I looked at this data. The first way I looked at my results was this table. I calculated the total momentum, so the momentum of the marble before the collision. I calculated the total momentum, so the block's momentum minus the marble's momentum after the collision. And then I calculated the percent change. So I did final minus initial over initial. And I found when I looked at these numbers, my initial momentum is consistently really, really close to my final momentum. These numbers are always really, really similar. And when I look at the percent change, these are really small. So they're all less than about 3%. And when I figure any errors I might have or uncertainties I might have in measuring, these are probably effectively the same. So this tells me that no matter where that marble hit the block, momentum was conserved. Another way I looked at the data was I put the total final momentum, so the momentum of the block minus the momentum of the marble, on the vertical axis of a graph, and the total initial momentum, so the momentum of the marble before the collision, on the horizontal axis. And I saw that these dots represent it, or come pretty close to falling on a line with a slope of 1. And so again, if I have that slope of 1, it means that the numbers on my vertical axis are equal to the numbers on my horizontal axis, which means that the momentum before the collision is equal to the momentum after the collision. So these are a few different ways to look at and see that the linear momentum was conserved in this collision, which fits with the interaction diagram that shows that there aren't any unbalanced interactions on this system that would cause this system's linear momentum to change. So what I was trying to get at with this portion of the lab is that linear momentum and angular momentum are completely separate. You can have, or whether the angular momentum is changing has no impact on whether the linear momentum is changing. And in fact, it turns out that if you define your system as the marble and the block, because you can think of that marble as moving relative to the system's axis of rotation and the system's center of mass, that marble does have some angular momentum before the impact. And if we calculated that, we'd see the angular momentum before is also equal to the angular momentum after. So we're going back again to this idea that as long as there are no unbalanced forces on your system, the system's momentum must stay constant.